Namaste friends, a hearty welcome to all of you for this session. Today in this session we will discuss a very important, interesting, fundamental and a popular theorem from geometry. Yes, it is Pythagoras theorem only. Pythagoras theorem has a number of proofs. So today in this session we will try to discuss a proof given by James A. Garfield. Garfield was the 20th US president and a mathematician, a very rare personality. Being a president of a country and contributing to mathematics is something unique. But it is so unfortunate that he was assassinated within 6 months after he becoming the president of US. We only wish that he would have lived longer so that he would have contributed to mathematics. Okay. To quote, "The truth will set you free. The truth will set you free, but first it will make you very miserable." This is one of its quotes. Okay. Now, to tell you something about Pythagoras theorem, this has more than 300 varieties of proofs are there. Friends, these 300 proofs can be broadly classified into 3 categories. Category number 1 is using the concepts of congruent triangles or similar triangles or sometimes both. The second category is dissection, dividing that area of a square into quadrilaterals and so on. And the very popular one is perigal dissection. Okay. The third and the final category is using the algebra, the concept of algebra, the identities. Okay, so whatever proofs we have got, all these things can be easily classified into one of these varieties only. Okay, let us draw the figure now. This is the line segment BC. Okay, so this is our line segment BC. At B, at the point B, let us drop a perpendicular like this. So let us mark this angle as 90 and call this point as A. Join C and A. You get a right angled triangle ABC in which angle ABC is 90 and therefore this AC is our hypotenuse. Now let us represent the lengths of these 3 sides of a triangle using smaller cases. Okay, that is, so the length of the side opposite to the angle A is BC. Let it be represented by the letter A, and the length of the segment opposite to this vertex B is AC. Let it be represented by the lowercase b, and finally the length of the segment AB, which is opposite to the vertex C, let it be represented by the letter C. So therefore now with this we can write down the data. So what is data? In the right angled triangle ABC, angle ABC is 90 degrees. So this angle is 90 degrees. Okay, so now we have to show that, we have to prove that A square plus B square, A square plus C square is equal to B square. A square means the BC square. C square means AB square is equal to B square means AC square. This is what we wanted to prove. So Garfield has thought in a different way. So if you see the construction, we can understand it. So this is the construction he has thought for this. So this is our figure as per our data. So first he says that extend this BC to a point E such that CE is equal to AB. Look at the figure carefully. So this is the point E such that the CE is equal to AB. So since AB is C units, the length of CE is also C units. This is the first construction. The second one is this. At the point E, we have to erect a perpendicular. So you can see at E, we are erecting a perpendicular. So perpendicular means this angle is 90. And here on this line, we have to choose a point F like this. So how this should be? It should be such that the length of EF should be is equal to BC. In such a way, we have to extend this. So EF is equal to BC. Therefore, EF also became equal to A units. Okay. So once we do all this, we have to join the points like this. F and C, F and A. So we need to join this F with C as well as with A. Let us do that. Yes. So F and C are joined, F and A are also joined. So this is the construction suggested by the great president of US, okay, Garfield only. Wonderful, wonderful construction. Can you see a beautiful quadrilateral has come now, namely A, B, E, F. What type of quadrilateral is this? Okay, for this, please observe these things. See, AB and FE are perpendicular to the same line BE. So assume that BE as the transversal. We know that if the sum of the interior angles on the same side of the transversal is 180 degrees, then those two lines must be parallel. Therefore, we can say that AB and FE are parallel to each other. So we have one pair of opposite sides is parallel. Then by definition, this quadrilateral must be a trapezium only. So ABEF is a trapezium. So with the help of the area of trapezium, Garfield has proved the Pythagoras theorem. So hearty congratulations to the departed soul. Many, many congratulations to him. A big round of applause for him. Okay. So having understood the construction, let us move further now. So in this figure, let us try to dissolve the hypotenuse AC as well as the segment, the CE also the hypotenuse. Okay, how it looks, my friends? So it is definitely a trapezium only. So can you recall what is the area of a trapezium? Okay, so we know that AB and FE are parallel because of the reason already stated. Can you tell me what is the area of any trapezium for that matter? Is equal to half into, yes, it is the distance between the parallel sides into, yes, you are right, the sum of the parallel sides. This is the formula for area of trapezium, which we will be using now in this proof. Okay, so therefore we can write it in the form of a formula. A is equal to, area is equal to half into H into A plus C in this case. So this is our formula we are going to use at the end. Now, so let us start the proof part. So this is our figure. Can you think of congruent triangles and see any pair of congruent triangles are in this? Yes. So compare right angle triangle, the angles and sides of the right angle triangle ABC and the angles and sides of right angle CEF. So you can see here. So this is the one right angle triangle ABC, and this is the another one. So we have to compare the angles and sides of these two right angled triangles, so that we will find out whether they are congruent or not. So the first point is this: AB is equal to CE. So this length of AB and CE are equal because of our construction. Point number 2 is, can you tell me which is the point number 2? Yes, angle ABC is equal to angle CEF is equal to 90 degrees. This angle is 90, this also is 90. This is because of data, this is because of our construction. Therefore, they are equal. And the final and the third point is BC is equal to EF. The length of BC is equal to the length of EF. This is on account of construction. Okay, we know that if two sides and an included angle of one triangle are equal to two sides and an included angle of another triangle, then those two triangles are said to be congruent. Therefore, we conclude that right angle triangle ABC is congruent to right angle triangle CEF on account of SAS theorem of congruent triangles. So we showed that these two triangles which are highlighted here are congruent on account of SAS. Now let's go to the next slide, please. Okay, now we have showed that these two triangles are congruent. So now let us consider the implications, andre ಪರಿಣಾಮಗಳನ್ನು ನಾವು ನೋಡೋಣ of the triangles being congruent ಆಗಿರೋದ್ರಿಂದ ಅದರ ಪರಿಣಾಮವನ್ನು ಪಟ್ಟಿ ಮಾಡ್ತಾ ಹೋಗೋಣ. So this implies that point number 1, AC is equal to CF. So the length of this hypotenuse must be equal to the length of this hypotenuse. This is implication number 1. Number 2 is angle 1 is equal to angle 3. For this you have to look at the figure. This is angle number 1. This is angle number 3, because these two right angle triangles are congruent, but they have a different orientation. For this triangle, BC is the base. For this triangle, C is the base. So definitely angle 1 and angle 3 are equal. And the third implication is angle 2 is equal to angle 4. Look at the figure. This is angle number 2. This is angle number 4. These two angles are also equal. Do you know the reason? Yes, because they are the corresponding parts of congruent triangles. Okay, so these are our implications now. Okay, but in this right angle triangle ABC, in this given right angle triangle ABC, don't you think this angle 1 plus angle 2 is equal to 90 degrees? Because sum of three angles of a triangle is equal to 180 degrees. So angle 1 is equal to angle 3. We have just now proved it. So in place of angle 1, let us substitute angle 3. So therefore angle 3 plus angle 2 is equal to 90 degrees. Now can you recall axiom number 1 and say that angle 1 is equal to angle 3, angle 2 is common, therefore angle ACF, that is this angle ACF, is equal to 90 degrees because they are the adjacent angles of a linear pair. This angle plus this angle is 90, this plus this 180, because this is a straight line, therefore this angle must be 90 degree. In other words, this also became a right angled triangle. So we have 1, 2, 3, 3 right angled triangles are there in this trapezium. Okay, now we will go to the next slide, please. Okay, so we have shown that this angle ACF is 90. Therefore, the length of CF is also equal to B units only. Okay, now Let us take up the area of the whole trapezium ABEF. The whole trapezium ABEF can be thought of as made up of three right-angled triangles. So therefore it must be equal to area of right-angled triangle ABC, that is this one, plus area of right-angled triangle CEF, means this one, plus area of this right-angled triangle ACF. So this plus this plus this will give us the total area of the trapezium. You know the formula for the area of trapezium. So let us write it as half into distance between the parallel sides. So BE is the distance between the parallel sides. So it is equal to A plus C into the sum of the parallel sides. So it is so nice, the parallel sides are also equal to A plus C only. So half into A plus C into A plus C is equal to, what is the area of any triangle for that matter? Half into base into height. Therefore, area of this triangle has to be half AC plus area of triangle CEF has to be half AC or of CA, one and the same, plus this one half into B, which is equal to half B square. So therefore, half into A plus C into A plus C is equal to half AC plus half AC plus half B square. Now we'll go to the next slide, please. Okay, so we have showed that this was the equation we were discussing in the previous slide. Let us simplify further. You can observe half is present as a common factor throughout on the left and the right. Therefore, let us cancel it out. Throughout, let us cancel this half. Okay, so A plus C into A plus C is A plus C the whole square, which is equal to AC plus AC here will become 2AC and this B square as it is. Friends, can we not expand this? This is of the form A plus B the whole square, which is equal to A square plus 2AC plus C square, which is equal to the right hand side as it is. Can you not cancel this plus 2AC and plus 2AC on either sides of the equation, so that we are going to get whatever we wanted to prove, which is A square plus C square is equal to B square. This is what we wanted to prove this. Hence it is proved. Hence it is established. Such a wonderful proof using the concept of the area of a trapezium Garfield has proved, friends. So to conclude, so this is what I did on a acrylic sheet. I have taken the printout of the image, and for the figure stickering has been done. So I can only say thank you very much for viewing this video. See you next time with another beautiful concept. Once again, thank you very much. Namaste.